Okay, welcome to the class. Today we're going to have a look at the second class in chapter 5. There's only one topic for today. We're going to talk about collisions. So imagine that you are in an amusement park. Chances that you have ridden in the bumper cars, where the objective is for you and your friends to crash into one another, which is shown here in figure 1. In the previous section, we have learned about two types of interactions within a system: collision and explosion, right? In this section, we'll learn more about different types of collisions, as well as what happens to the energy of systems when a collision occurs. How can you use what you have learned about linear momentum and kinetic energy to understand what happens when two bumper cars collide and bounce apart, and what happens when they collide and stay together? All right, so there are two types of collisions, which are elastic and inelastic collisions. In the previous section, we have learned how to analyze a system of two objects. The total momentum of the objects before a collision is equal to the total momentum of the objects after the collision, right? In this section, we'll apply the law of conservation of momentum to analyze several different types of collisions. In general, a collision changes the velocities of the objects involved. The final velocities, those found just after the collision, are different from the initial velocities from just before the collision. Since the kinetic energy of an object depends on its speed, the kinetic energy of the object also changes as a result of the collision. Collisions fall into two general types, depending on what happens to the total kinetic energy of the entire system. They are elastic and inelastic collisions. Okay, so in elastic collisions, the total kinetic energy is reserved, which means the initial total kinetic energy should equal the final total kinetic energy. Whereas in inelastic collision, the total kinetic energy is not conserved. But in both cases, the total momentum should be reserved. Okay, now let's have a look at the first type of collisions, which is elastic collision in detail. In an elastic collision, the system's kinetic energy is conserved. That is, the total kinetic energy of the two objects after the collision should be equal to the total kinetic energy of the two objects before the collision. This is called conservation of kinetic energy. The term elastic can help you understand how and why a collision affects the kinetic energy. For example, an extremely elastic ball, such as a rubber ball, is compressed during a collision, and compression stores energy in the ball just as energy is stored in a compressed spring. In an ideal rubber ball, all of this potential energy is turned back into kinetic energy when the ball decompresses, just like the springs come back at the end of the collision. So figure 2 here shows two rubber balls before and after a collision. So note here, in elastic collisions, both the momentum and kinetic energy are conserved. Any questions? Okay, on the contrary, in inelastic collisions, Inelastic collisions are collisions in which some kinetic energy is lost. The kinetic energy is transformed into other forms, such as thermal energy or sound energy. Consider a collision involving a ball composed of soft putty or clay. The ball will not spring back at the end of the collision. The energy is absorbed, causing the kinetic energy after the collision to be less than the kinetic energy before the collision. The collision, therefore, is inelastic. Okay, in a summary, we have the following statement. In an elastic collision, both momentum and kinetic energy are conserved. Whereas in an inelastic collision, momentum is conserved, but kinetic energy is not conserved. Note that in both types of collisions, the momentum is conserved. The total energy is also conserved in both cases. Even the kinetic energy is not. Any questions? Okay, I'll give you 1 minute to have a look at this graph here. This compares the two types of collisions, elastic and inelastic. Okay, then there are two subtypes in elastic collisions, which are perfectly elastic collisions and there are two special types of collisions, which are perfectly elastic collisions and perfectly inelastic collisions. A perfectly elastic collision is an idealized situation where friction and other external forces are negligible. And therefore, momentum and kinetic energy are perfectly conserved. On the other hand, a perfectly inelastic collision is one in which the two objects in a collision stick together after the collision, so that the objects have the same final velocity. Perfectly elastic and perfectly inelastic collisions occur in isolated systems in which the effects of friction and other external forces are negligible. Perfectly elastic and perfectly inelastic collisions are extremely rare in the world around us and represent idealized cases. Most real collisions fall somewhere between these two extreme situations. However, it is useful to consider perfectly elastic and perfectly inelastic collisions as ideal examples of Newton's laws. As we do this, be mindful of external forces that might additionally affect the systems. Okay, so first let's have a look at perfectly elastic collisions. By applying some basic assumptions, you can use collisions with billiard balls, bumper cars, and asteroid planet systems as reasonable examples of perfectly elastic collisions. In perfectly elastic collisions, remember both momentum and kinetic energy are conserved. In other words, we have the following two relationships. The initial momentum should equal the final momentum, right? Also, the initial kinetic energy should also the kinetic energy in the final state. In one-dimensional collisions, each vector can point in only one of two ways. Designate directions in a way that is convenient for solving a particular problem. For example, we may choose to assign right as positive and left as negative, right? Then we can express the vectors using only their magnitudes, understanding that a negative value implies a left direction. Okay, next, let's have a look at some sample problems in which we can use these equations to explore perfectly elastic collisions in one dimension. Okay, now let's have a look at this sample problem here. Analyzing perfectly elastic collisions. Well, suppose we have two balls with different masses involved in a perfectly elastic collision. Ball 1 with mass m1 equals 0.26 kilograms, traveling at a velocity v1 equals 1.3 meters per second, that with direction as right. Collides head-on with stationary ball 2, which has a mass of m2 equals 0.15 kilograms. Can you determine the final velocity of both balls after the collision? Okay, I'll give you 5 minutes to have a look at this question here. Then we'll have a look at the solution together. Okay, note that this is a perfectly elastic collision, right? So in a perfect elastic collision, both the momentum and kinetic energy should be conserved. You can use these two types of relationships to solve this problem. Okay, you can start now. All right, have we finished? Okay, because this is a perfectly elastic collision, right? So both the momentum and kinetic energy should be conserved. Therefore, this question asks us to find the velocity of the both balls after the collision. Note that there should be two unknown quantities, right? From the statement that the momentum is conserved, we should have a first equation, right? And from the statement that the kinetic energy is also conserved, then we have a second equation. So basically, this problem involves two unknown quantities, and you have two equations. So we should be able to solve these two unknown quantities, right? Also, this is a one-dimensional problem, so we can designate the right as the positive direction. So if you have the velocity as a positive number, then the direction should be to the right. Otherwise, if you have a negative number, the final velocity would be a velocity that is pointing to the left, right? Okay, so we can use these two equations to solve these two quantities. First, use conservation of the momentum to solve for VF in terms of VF2. Sorry, to solve VF1 in terms of VF2. That means to eliminate one of the unknown quantities, right? Note that we have M1 VI1 plus M2 VI2 equals MV VF1 plus M2 VF2. Isolate the term containing VF1 on the left side of the equation, since VI at VI2 equals 0. The equation becomes M1 VF1 equals M1 VI1 minus M2 VF2, as shown here. Then we can divide both sides by M1, in which we have VF1 equals VI1 minus M2 over M1 times VF2. And put all the values in, we have VF1 equals 1.3 meters per second minus 0.58 VF2. So let's call this as equation number 1. We'll use equation number 1 later. The conservation of kinetic energy equation can be simplified by multiplying both sides of the equation by 2. And noting that VI2 is 0, right? So this gives us a simplified form, which is M1 VI1 square equals M1 VF1 square plus M2 VF2 square. So let's call this equation number 2. Then we can substitute equation 1 and the given values into equation number 2. So then expand and simplify both sides of the equation. And eventually this gives us 0 equals negative 0.9 at 0.39 VF2 plus 0.24 VF2 square. So here we have obtained a quadratic equation in terms of VF2, right? So we can easily solve VF2 from this quadratic equation. You can use either the factorization method or just use the quadratic formula, right? So the factor of VF2 from this equation, we can get VF2 is 0 meters per second, or the other solution is 1.63 meters per second. Well, in the situation where VF2 equals 0, this describes the system before the collision, right? The equation has a second solution describing the system after the collision, which gives us 1.63 meters per second. That should be your correct VF2. Then we can substitute this value into equation number 1 and calculate the final velocity of ball 1, which gives us VF1 equals 1.3 meters per second minus 0.58 VF2. Then VF1 should equal 0.35 meters per second. So the second ball has a final velocity of 1.6 meters per second. Direction is to the right. And the first ball has final velocity of 0.35 meters per second. Direction is also pointing to the right. Okay, so basically we have two unknown quantities and two equations. We should be able to solve two unknown quantities here. Any questions? Okay, so the analysis and solution used above apply to the special case of perfectly elastic collision, where one body is initially at rest. A more general case of perfectly elastic collisions involves two bodies that are already in motion before the collision. Collisions of this type will be explored in greater depth in later sections of our class. Okay. Okay, so next let's have a look at the other special case, which is a perfectly inelastic collisions. And before we dive into this, we can take a 10 minutes break. Okay. Please return before 15 past 10. Oh, sorry, 5 past 10, and we'll talk about the perfectly inelastic collisions. Okay, you can take a break now. Okay, let's continue our lesson. Next, let's have a look at the perfectly inelastic collisions. The simplest type of inelastic collision is a perfectly inelastic collision, in which two objects stick together after the collision, so that the objects have the same the same final velocity. If the colliding objects bounce, it is not a perfectly inelastic collision. A good example of a perfectly inelastic collision is one in which two cars lock bumpers. So here, figure 4 on this page shows two cars coasting on a straight road in one-dimensional space with velocities vi1 and vi2. These are the two initial velocities of the two cars. Then the cars collide and lock bumpers, and they have the same velocity, vf, after the collision. The cars are moving in a horizontal direction, x, and if they are coasting, there are no external forces on the car in this direction. Therefore, the total momentum along x is also conserved. So in this case, the condition for conservation of momentum along x is given by the following formula here. The left side is the initial momentum of the two cars, mv vi1 plus m2 vi2. The right side is the total momentum of the two cars in the final state, which is given by m1 vf1 plus m2 vf2. In this case, there is only one unknown, the final velocity vf, right? Since two cars are stick to each other, so they'll have the same velocity in the final state. So we can solve the above equation for vf. This gives us m1 vi1 plus m2 vi2 equals m1 plus 2 times vf. Then the final velocity for either car, vf, is given by m1 vi1 plus m2 vi2 over the sum of the two masses, m1 plus m2. This equation relates the final velocity of the two objects in a perfectly inelastic collision to their masses and their initial velocities, just here. And we can apply this equation to solve some related problems in our real world. Okay, next let's consider a sample problem here. This illustrates how we can apply the conservation of momentum to a one-dimensional, perfectly inelastic collision. Okay, suppose two cars, a sports utility vehicle or SUV of a mass of 2,500 kilograms and a compact model of mass 1,200 kilograms are coasting at a constant velocity along a straight road. Their initial velocities are 40 meters per second heading west and 10 meters per second also heading west, respectively. So the SUV is catching up to the compact car. When they collide, the cars lock bumpers. Assume no external forces exist along the direction of travel and total momentum along x is conserved. Can you determine the velocity of the two cars just after the collision? Okay, I'll give you 5 minutes to consider this question by yourself, and then we'll have a look at the solution together. Okay, you can start now. All right, let's have a look at the solution together. So the two cars stick together after the collision. So this is an example of perfectly inelastic collision. In this system, both vehicles are moving in the same direction, which is to the west. So we can use VF equals MVVI1 plus MVVI2 over M1 plus M2 to calculate final velocity, which is shown here. Just put all the numbers in. We have 2,500 times 40 plus 1,200 times 10 over 1,200 plus 2,500 plus 1,200. So this gives us the final velocity of either car. Vf equals 3 times 10 raised to the power of 1 meters per second. And the direction is due west. So we can make the final statement like this. Final velocity of the cars is 3.0 times 10 raised to the power of 1 meters per second with direction due west. Any questions? No? Okay, let's have a look at another sample problem here. A child with a mass of 22 kilograms runs at a horizontal velocity of 4.2 meters per second forward and jumps onto a stationary rope swing of mass 2.6 kilograms. The child sticks on the rope swing and swings forward. A, determine the horizontal velocity of the child plus the swing just after the impact. B, how high do the child and swing rise? Okay, again, I'll give you 5 minutes to consider this question by yourself. And we'll have a look at the solution after that. Okay, you can start now. All right, let's have a look at the solution together. Okay, this is another one-dimensional perfectly inelastic collision. We can let M1 and VI1 represent the mass and initial velocity of the child, and M2 and VI2 represent the mass and initial velocity of the swing. We know M1 is 22 kilograms, VI1 is 4.2 meters per second forward, M2 is 2.6 kilograms, and VI2 is 0, right? And then, because this is a perfect inelastic collision model, so we can use VF equals M1 VI1 plus M2 VI2 over M1 plus M2 to determine the final velocity just after the child collides with the swing. Put all the values in, we have VF equals 3.76 meters per second, direction is forward. So we can make this statement here. The child and rope swing have a final velocity of 3.8 meters per second, direction is forward, just after the collision. In question B, note that conservation of energy requires that the initial kinetic energy of the child and swing transform to gravitational potential energy at the highest point of the swing, right? Which means EK equals mg delta y. If we choose the lowest point as a reference point, where the potential energy due to gravitational force is 0. So this equation gives us 1/2 times the sum of the two masses times VF squared equals the sum of two masses times G delta Y. Then we can cancel M1 plus M2 to both sides. This gives us delta Y equals VF squared over 2G. Because we know the values for VF and also we know the gravitational acceleration G. Put all the values in, we have delta Y equals 0.72 meters. So the child and rope swing will rise to 0.72 meters above the initial height. So the initial height is our reference point, where the gravitational potential energy is 0. Okay, do you have any questions? Right, if no questions, that's the end of today's class. So basically we have talked about the collisions today, right? There are two broad types of collisions, elastic and inelastic. And two special cases are perfectly elastic collisions and perfectly inelastic collisions. So in elastic collisions, both the momentum and kinetic energy are reserved, whereas in inelastic collisions, only the momentum is conserved. Okay, remember to complete your homework and submit them before the deadline onto Google Classroom. Okay, I'll see you next time.